All right, good morning, everybody, and thank you, Pam. Again, my name is Darren Wright. I'm the high performance housing specialist here at the PHRC. A little bit of background about myself. I know I've probably talked to a lot of you, or you have been in my webinars before, but my background is within the residential field exclusively. I've really never done any commercial work. I have, project manager, own some businesses. Builder in the South, Charleston, South Carolina, Asheville, North Carolina, and done some here in Pennsylvania as well. Worked as an educator for a number of years in the field. So my background's pretty varied. I'm coming at this really from a builder's perspective, mostly, and an educator's perspective. So the title itself is Mastering Exterior Insulation. I'd like to say you're not going to be able to leave here and understand everything there is to understand about exterior insulation. This is really realistically is going to be an introduction to exterior insulation, but really also how navigating the PA's new UCC code and insulation interact with each other, and how that's being affected. Again, we'll do a little bit of housekeeping here. Again, some of these slides are for AIA compliance information, what we got to do to make sure that we can get you guys your credits. We have a program description here. Like I said, this webinar will explore the latest updates in the Pennsylvania UCC, specifically concerning continuous exterior insulation. You learn about key changes, compliance strategies, and best practices to optimizing energy efficiency to meet the new energy standards. And hopefully, whether you're a contractor, architect, building professional, this webinar will provide some essential insights to keep your projects up to date and then moving forward, transitioning into the new codes. Here's some learning objectives. Again, understanding UCC, identifying compliance strategies, and gain some insights and realistically how this is going to affect us moving forward. Basic fundamental questions. What is the PA-UCC? What is changing? When is it changing? And where do I go from here? So the beginning part of this, I'm going to sort of talk about this a little bit so we all understand what the UCC is and how it came about, how these changes came about, and how they're being affected specifically about exterior insulation and really the fenestration and insulation table, and how to gather more information about these things. A quick introduction to the UCC. If you're a code official, this is going to be something you really understand already. But for people who are like the educators, some of the builders and remodel, you might not completely understand what the UCC is, the PA-UCC specifically, and how it relates to codes. The PA-UCC is the Pennsylvania Construction Code, Uniform Construction Code. And it's made up of multiple parts. It's basically, in a nutshell, it's a combination of the IRC, the 2021 IRC, amendments created by the RAC, and then statutory amendments. And when we talk about statutory amendments, what we're talking about are legislative amendments. These are permanent changes to the building code, and they're voted on at the legislative level. So they don't change from year to year unless it goes back to the government, and then they take a vote on it, and then it changes that way. So you can imagine the difficulty of adding or subtracting statutory amendments from the UCC. So they stay kind of consistent year after year. Amendments by the PA-UCC Review and Advisory Council, the RAC, they that happens every time we go into a code change year. They'll review the IRC coming in, and they will make their recommended changes or how to adopt the IRC, to Pennsylvania specifically. And again, we're transitioning from the 18 to 21 this year. And the UCC, like I said, is made up of three parts: the IRC, statutory amendments, and the RAC amendments. And then The rack amendments are something that I believe if you haven't done so already, would be a good idea to go and actually print yourself a copy because it's going to be very beneficial to you to have. I have a paper copy and I'm going through it more and more. Um, it's hard to read online because I don't read online very well, but I would recommend printing that out. And then when you get your new IRC book, if you are going to get a hard copy, to keep that with that, because you're going to need to reference back and forth. And it's a really good idea to go ahead and read the IRC, the rack amendments, I'm sorry, ahead of time. I think it's about 50 pages. Not all of them deal directly with the IRC, but it's a good idea to go in there and sort of take a cursory look at it and kind of pick out things that you think will affect you, and then you can sort of dive into those a little bit deeper. And what are these changes happening as far as how it's going to affect us? The launch date for the let me advance the slide here. July 13th is when they take effect. There is going to be a phase-in period, and that's going to be a 6-month phase-in period right here. So what that means is if you have a contract signed and in place by that July 13th date, you have 6 months from that date, and that would come to January 12th to actually apply for a permit. And so if you do that within that period, you're still fall under the 2018 code. If for some reason you sign a contract on July and you keep pushing off the date until you pull your permit, and that permit gets pulled on January 13th of 2026, you're now automatically pushed into the 2021 code cycle. So you're going to have to do a lot of redesign or whatever it is that you're going to have to do to become code compliant at that point changes. So it's really important to pay attention to these dates, and know where you are in the phase of construction and permit pulling moving forward, at least for this year. Currently, this is our climate zone map. We all should be familiar with this. Pennsylvania has 4, 5, and 6 currently. Most of the state right now is 5. I'd say 3/4 of it. 2/3, 3/4 of our state is climate zones 4, 5, and 6. And this is the current table we're following. And you can see here, 4 and 5 and 6, we do have, R20 wood, our wood frame wall R values is what we're going to be talking about today. And currently we have an R20 cavity insulation for 4 and 5 and 6. And then you can see 13 plus 5. And so what that means is you can have an R13 wall cavity with a 5 continuous insulation on the exterior. So continuous insulation is currently part of the code language. Not many people are using it because it's still relatively easy to meet that R20 wall cavity value with off the shelf bat insulation. So it really is easier right now to follow the code. We are moving to a new code map as well, a construction zone map, I'm sorry, I should say. And this is what the new map is going to look like. Pennsylvania loses zone 6, and now we're exclusively zones 4 and 5. And again, I'd say mathematically, we're still probably 3/4 between 2/3 and 3/4 of Pennsylvania will be construction zone 5, and then the lower right hand, the lower southeastern side of Pennsylvania is going to be construction zone 4. We are losing construction zone 6. And this is what the new insulation and fenestration table will be for us moving forward. If you look at this table and then you look at the 2021 IRC code book, they're not going to match. This is one of the changes that was adopted by the RAC, and this is a table exclusively found within that RAC amendment. So this is one of the reasons why you want to make sure that you print that RAC amendment out and keep it with your code book. Because if you just follow the IRC, you will be code compliant. It's just you are going to be overbuilding or exceeding the minimum requirements within Pennsylvania if you follow that code. So just be aware of that. This table is exclusively to the rack amendment and it's not found in the IRC 2021. Question, what is continuous exterior insulation? Obviously it's exactly what it sounds like. It's a layer of thermal insulation installed on the exterior side of a building's wall assembly without any gaps, breaks, and it goes across the entire structure. So, so there theoretically should be nowhere on the exterior except at your fenestrations, at your windows and doors, where this insulation isn't covering the exterior of your building. And why? Why? What are the characteristics of continuous exterior insulation? Like I said, it's installed on the outside of the building structural frame. You can almost picture it hanging on the exterior side of the building. And it's there to cover all of that. You're making sure all your headers are covered, your sills, anything that there's a thermal bridge, potential thermal bridge, where continuous exterior insulation is there and it's designed to mitigate that thermal bridging. It's usually placed between sheathing and cladding or sometimes directly over the framing. Obviously, if it can be used potentially for without your sheathing, then there's a whole bunch of other considerations that you're going to have to be that are going to have to be taken into account because if you're going to try to eliminate your sheathing and just use this as your sheathing, there's other engineering issues that you're going to have to come up with that are going to be required to deal with racking and other issues. But for the most part, it's going to be applied directly to your sheathing or somehow applied to your sheathing and then underneath your exterior siding. And like I said, it's just there to help eliminate thermal bridging. The benefits, it reduces thermal bridging. We're going to talk about that here in a little bit and what that means. It improves your envelope performance, making a more comfortable home. And then it does come into moisture and vapor management and condensation mitigation as well. So, it does help thermally. Yeah, I think that would be the main consideration when we talk about continuous exterior insulation. But we can't forget about other things that are affected by this insulation as well, positively and negatively. And we'll talk about those moving forward as well. First, though, a little bit about reducing thermal bridging. Getting into a little bit of building science here and just an explanation of how this stuff works. Thermal bridging, material with a lower R value, allowing heat to pass through the assembly with a much higher overall R value. We talk about thermal bridging, and you ask the question, where does this happen? It basically happens in portions of your wall assembly that are insulated. And then the most common example of this is our wood stud wall framing. And if you're into performance methods of building where you're doing the mathematical calculations of your R value and your insulation within your wall cavity, and we talk about advanced framing and your framing factors, thermal bridging if is affects your framing factor. When we talk about framing factors, we're talking about how much wood, say 25% of your wall assembly is made up of framing. That's 25% of your wall assembly that's not insulated, and that's 25% of your wall assembly where that thermal bridging can happen. And that's a big portion of your wall assembly. So yeah, you might be insulating very well within those cavities, but you also got to consider everywhere that is not insulated, it's a potential point for lowering your overall thermal value of your U value of your wall assembly. And like I said, the most common place people understand thermal bridging and where this happens is in the framing portions of our wall assembly, the wall studs, the sill plates, the top plates, and so on and so forth. And this is kind of a thermal picture of what this looks like. This is on the interior side of a house. And you can literally see the studs and where that thermal bridge is happening. And continuous insulation is there to help with this and help mitigate this kind of stuff. We want to try to create bridges or eliminate bridges where this is happening. And you can see the top there, that's where the the double top plate happens. And there's probably other factors in there. Maybe that gap between those double top plates wasn't sealed properly. So we're also getting maybe a bit of air infiltration up there, and that's also causing a larger thermal bridge that's, thermal contamination, however you want to describe that, at the top of that wall assembly. We can't talk about any of this stuff without understanding what heat flow is and and how heat flow works within our home. Heat obviously is going to move from warmer to cold. And when we talk about heat flow, when we talk about wall assemblies, it's happening mostly what we call conduction. There is a little bit of convection happening in our wall assemblies, especially if we use a batt insulation. And convection happens with an wall assembly just as air moves, because fiberglass insulation is not a great air barrier. Air can actually pass through it with relative ease. So if we have a little bit of an airflow in there, heat can actually air can actually circle within that wall cavity, and we can get a little convection effect happening. But most of that is happening through conduction, direct contact of that wall to the exterior and to the interior, and it transfers through connections. Actually, that's where thermal bridging comes in. And radiation really only happens when we talk about fenestrations, windows, and things like that. This is our conditioned space. This is obviously the conditioned space, and this is not including the basement, but a lot of times now the basement will be a part of your conditioned space. And in the wintertime, this is where the heat flow happens. We're trying to keep that heat on the interior side of our house and keep it from escaping to the exterior. Economically, that the better we are at this, the better performing our houses are going to be. And that's just a benefit in many different ways. Financially, environmentally, reducing your carbon footprint if that's what you're into, But yeah, heat flow in the winter is moving from outside to inside. And obviously inverse to that in the summertime, we have heat flow moving from the exterior to the interior. Pennsylvania, we are a kind of an interesting climate. Living down south, we were mostly concerned, especially on the coast and the farther south you go, you're concerned with air conditioning. We're mostly concerned with how to keep our houses cool. The farther north we go, like if we were to go up into Alaska to northern Minnesota, we're in a more of a heating-based climate. Pennsylvania, we live in an environment where in January we can have a couple of weeks of below freezing weather. It doesn't happen every year, but it definitely can happen. And then the summertime, we can have a month of 90 plus weather with very high humidity. So when we design and build our wall assemblies and construct in this environment, we are building to a broad range of environmental factors, damp, wet, dry, hot summers. It's just, we run the gamut here in Pennsylvania. I think it makes it a little bit more challenging when we talk about thermal protection and things like that within our environment. And here's just a little math, if you're a math nerd, how this works. Can you stop heat flow? That's the question I really want out of this slide. No, we can't completely stop the flow of heat from warm to cold. It's going to find a way through. It might take a very long time to get there, but it will continue to move in that direction. So what we want to do is, therefore, we want to help slow that down, and eliminating thermal bridging is one factor that goes a long way into slowing that heat loss down, that movement of heat from warm to cold. Like I said, when a thermal gradient is present, heat flow cannot be stopped, but can be managed by installing thermal insulation. And right now, where for most wall cavity insulation, heat will always flow through the path of least resistance. And again, that's referencing the path of least resistance in most building envelopes is the framing wall assembly as well as window and door assembly. But what we're going to be talking about today is managing heat flow through the building envelope itself. Um, and I talked about this at all. Framing factor defines the proportion of framing in an insulated wall system. You know, jack studs, top plates. And some of this stuff is mitigated naturally already through best building practices. People are starting to install insulation in our headers. We're getting these engineered headers, which allow us to install up to 2 inches of foam board insulation. So there are places within the building envelope that within the framing system that are already mitigating that heat loss. But moving forward, like typical framing factor, it says here is 25%. Through advanced framing practices and things like that, you can actually get that down pretty low. You can get that down to like 19 or less in some places. So it doesn't seem like that big of a number, but the bigger the house is, the better, the lower that number, the better your overall thermal R value is going to be. And again, how do we manage this? Providing a thermal break. Um, and obviously you're tuned into this webinar. So our thermal break to that bridge is going to be continuous exterior insulation. And again, you can reduce this number by lowering your framing factor by advanced framing techniques. But for the most part, what we're going to talk about, and we can talk about that in later webinars. I think we are going to be talking about that in later webinars, how to reduce our framing factor to help with this. But today we're going to be talking about continuous insulation. The way we talked about, thermal properties that we had to deal with, that continuous insulation dealing with, and I want to get into the moisture or the vapor management side, because this is just as heavily affected, in my opinion, as the thermal topic. This definitely is a thermal. When most people think of continuous exterior insulation, they just automatically think of the R value and how it's going to make this a thermally better wall assembly. But you really got to be careful and consider the moisture and the vapor management as well when we talk about continuous exterior insulation. Because quickly, I'm going to show this quick slide here, because what we're concerned about when we talk about moisture management and vapor management, what we don't want to do, what we're doing when we talk about those things, is eliminating the possibility of condensation within a wall assembly. Having vapor pass through that wall assembly and coming in contact with a cold surface and creating a point where water can condense. And then within your wall assembly, you now have moisture. And we all know what moisture in a wall assembly can lead to, if it doesn't have a way of getting out, is mold and rot. So the 2021 IRC, specifically R702.7, talks specifically about vapor retarders. And we're going to go through this a little bit here. Specifically, it'll become more clear as I get going why I'm referencing this and talking so much about this. This is what the new 2021 IRC table looks like. Section looks like R702.7. Vapor retarders. There's still the exceptions down there in the bottom. Basement walls, below grade portions of any wall, and those sort of exceptions are the same. The first part here is vapor retarder materials shall be classified in accordance with table R702.7, number 1. I think the biggest change to the vapor retarder section of the IRC is they've sort of cleaned it up and made it more user-friendly. They've added more tables, and there's better, in my opinion, better information within those tables. It's easier to navigate for people who aren't very understanding or have a clear understanding of what vapor retarders are and the importance of paying attention to what those do within your wall assembly. So the first table here is 702.7, number 1, materials and classes. This is a really good um, table, in my opinion, because it breaks it down into not only what class of vapor retarder there are, it shows you like there are three classes of vapor retarder we're talking about here, class one, class two, and class three. And it actually gives samples of those class one vapor retarders. It doesn't list them all, obviously, but this is a good starting point for people to understand, like what is a class one sheet poly? Oh, we all kind of know what that is. So that is a class one vapor retarder. Gets you an idea, like when we talk about class one, that's the most restrictive. And then we get down to class two, that's less restrictive. Class one's anything from 0 to zero point 0.1 permeability, pretty low. Then we get to class two, and we get to the normal things that we understand about uh, vapor retarders and insulation. Our craft facing on our fiberglass insulation is one of those. That's a class two vapor retarder. And there's other things listed in here. And class two goes from 0.1 all the way up to 1. And then we get into class three vapor retarders, which is the most open. Um, and that's things like latex paint. And there's certain foam boards and other things which we'll talk about, especially when we talk about exterior continuous insulation, are class three vapor retarders. But this is a good point. We have three classes, one, two, and three, and this gives you sort of examples of what those are. The next table that you're going to see when we talk about vapor retarders, vapor retarder shall be provided on the interior side of frame walls of the class indicated in table R702.7 number 2. Um, and this table just breaks down what we are allowed to use within our climate zones. And right now we are climate zones 4, 5, and 6. And so if you look on here, and we're transitioning to climate zones 4 and 5, so you can see like right here, this is us now with this table, the second table, this is where we are. You can see class 1 in construction zone 4 is not permitted. And again, going back, class 1 vapor retarder is sheet poly. We've seen this before in the past. Maybe in the 80s, if you've been in building long enough, you might have gone in and had to fix situations where people used to use a class 1 vapor retarder on the inside of wall assemblies, especially in the 70s and 80s before we understood it and what those problems were created by using that. Right here, they're saying you cannot use a class 1 vapor retarder in construction zone 4. You can use it in construction zone 5. It is permitted, but there's a little note there. It's an appendix B. I don't know if you can see my cursor, but it's permitted with B. If you look down here at the lower portion, there's a note B, use of a class 1 interior vapor retarder in frame walls with a class 1 vapor retarder on the exterior. And this is where continuous exterior insulation starts to become a factor when we talk about vapor retarders. If your use of a class 1 interior vapor retarder in frame walls with a class 1 vapor retarder on the exterior side wall shall require an approved design. Yes, you can do that. It could be dangerous if you're not doing a lot of things to help control moisture and vapor at this point, but it is permitted, but you have to get it approved ahead of time. You can't just do it. This, I should say this as well. This is the 2021 reference. If you look at 2018, right now, there is no note B. It's just permitted. So it is permitted. Hopefully at this point, we've all understood and learned like what are the dangers of using a class 1 vapor barrier on the interior side of a house, especially in construction zone 5. If you're up in zones 6, 7, 8, and you're up in Alaska, that's a whole different conversation, but we're talking specifically to Pennsylvania. Yeah, so this is the second part of the second table within when we're talking about vapor retarders within the new 2021 IRC. And here's back to the reference of that chart again, the fenestration and insulation table. And again, you can see down there, uh, construction zone 5. I'm just going to reference that because that's most of the state. it's R23, and down there R13 plus 7.5 continuous exterior insulation, or R20 with 3.8 continuous exterior insulation. I'm going to say, yeah, you're not going to find 3.8. So realistically, that's going to go up to like an R5. I will give some examples of exterior insulation that aren't 5. They're, but well, for the most part, we're most familiar with just, going to Lowe's and seeing 4x8 sheets. And then most of those are R5 per inch. And why does this matter? Um, and here's a wall diagram of what's currently allowed. This is, if you follow current code standards 2018, this is an assembly that you can see out there that is allowed by code. And how I think they're trying to kind of help mitigate these situations. All right, it's a 2x6 wall with 1 inch of R6.5 polyiso exterior foam insulation. And on the interior side, you can see you have your drywall, and you can see there's a fiberglass insulation with 4 mil poly on the interior side. By current code standards, this is a code compliant assembly. The problem with this assembly is there's nowhere for this wall assembly to dry. You have a class 1 on the interior and the exterior of this wall assembly. So if somehow moisture does find its way into that wall cavity, especially with fiberglass, it's not going to get out. And once it's in there and it gets onto your OSB, you're gonna run into mold problems. I believe you will have negative consequences with this wall assembly. And again, this is currently code compliant. So what we want to do is be careful, currently, obviously, moving forward, but make sure that when we're referencing these things and reading these notes, that pay attention to not only the chart but the little notes below it as well. And again, this is the second part of the vapor retarder when we talk about their new charts moving forward. Okay, third part here, including compliance with tables 702.73 and 4 were applicable, and approved design using acceptable engineering practices for hygrothermal analysis shall be permitted as an alternative. The climate zone shall be determined in accordance with section, I showed you the chart where our climate zones are. And again, quickly, we've seen these two charts already. This is 1 and 2, and we're going to move into 3. And this is where exterior insulation becomes a little bit more of a factor. It becomes a little bit more into play, especially when we talk about class 3 right here. You can see in construction zone 4 on the second chart, a class 3 vapor retarder is permitted in construction zone 5, but you have to reference the table. So, and that's important. And what we're doing here is when we reference a table, it says here, one of the things that's permitted is you can use a class 3 vapor retarder in construction zone 5. And down here at the bottom here of this first chart, it says continuous insulation with an R value of 5, less than 5, greater than 5, over a 2x4 wall assembly, and continuous insulation with an R value of 7.5 or greater in a 2x6 wall assembly is permitted. And this gets you into where you are now allowed to use a class 3 vapor barrier on the interior side. So if you want to be sure, like if you want to use a class 3 on the interior side, you have to make sure you're following what's compliant as far as continuous exterior insulation on the exterior. And if you look at the chart, the new chart down here, if you just follow current code, the new code, you're going to be within that range. Because it says if you're going to have a 2x3, right here you can see if you're having a 2x4 wall assembly with R13 interior cavity insulation, you have to have an R5 already. That's going to be the new code. And if you're using a 2x6 frame wall and you're putting R20 insulation in there, you need 3.8. Now that doesn't get you up to 7.5, so that could be an issue there. But most of the time, um, you're not going to be using, you can't find R 3.8. So you're going to automatically having to be use a heavier insulation on the exterior side of this. But understand, yeah, you can reference this chart, but the insulation referenced here does not supersede the fenestration table. You have to follow the fenestration table. The uh, insulation and fenestration table is the one that takes precedent over anything else referenced in the code. Yeah, here it talks about the requirements in this table apply only to insulation used to control moisture in order to permit the use of a class 2 vapor retarders. The insulation material used to satisfy this exhaustion also contribute, but do not supersede the thermal envelope requirements in Chapter 11. So just understand that you still have to meet code as far as Chapter 11 is concerned. And what does this, what does this do? Continuous insulation and how is it affecting our vapor? Obviously vapor drive in winter is moving through your house. It's moving from the interior side to the exterior side. It's moving from a warm environment to a cold environment. So it's passing through your wall assembly. Um, you want to make sure, how this affects you is realistic. It comes down to condensation and the potential for condensation within your assembly. And this all is going to come into reference in how to help mitigate those things. And here's one example of a wall assembly. We have a 2x6 wall with 1 inches of R5 XPS exterior sheathing. You have our fiberglass insulation, craft insulation with a craft facing. We have our drywall, and you can see your vapor is passing through that assembly. It's getting into your insulation. It's heading to your exterior side of your wall assembly. And the question is this a good designed wall assembly? Um, yeah, I mean, we can look at this and you can see here, 1 inch of R5 XPS, I believe, is a class 2. Yep, it's a class 2 or 3, dependent on product. You really want to pay attention when you're reading these. This is as important if you're using exterior sheathing, you're building multiple houses and having these conversations with your crew. If you have a new crew member installing this insulation on the exterior side, I just want to say this as a reference, and say they run out and they call you and say, hey, we're out of insulation. We're 4 sheets short. And you could say, yeah, go get 4 sheets at Lowe's, charge it, and then keep going. You want to make sure that they understand. We'll talk about this a little bit. Is those sheets have different vapor permeability ratings. It might be the same thickness, but you might jump from a class 2 to a class 3 rather quickly and not even realize you've made that mistake. I think I'm hitting the wrong button here. Yep, sorry, I did that. So, what does this assembly look like? Is this a good assembly? Remember where your throttle is. Is this code compliant? Yes, it is code compliant. I think the throttle, the most restrictive part of this wall assembly is going to be the craft face insulation, because that is a class 2 vapor barrier. Their 1 inch of rigid XPS is a class 3, so that's very vapor open. So realistically, this wall assembly is good in a couple different ways. It's a good thermally, but it also is good because it can dry both to the exterior and to the interior. So yeah, I believe, like, you want your wall assembly to dry in both directions ideally. You don't want to put a throttle in there that is going to eliminate one direction of the ability for your assembly to dry. That's why I said if you send somebody to replace that missing 4 sheets of rigid foam and they come out with a foil-faced insulation, that's a very restrictive class 3 vapor barrier. So, and if they happen to put that on the portion of your wall assembly that's outside of a bathroom, you can see how that could become a really big issue because you're in a very damp environment and you're putting the wrong insulation in the wrong spot. And you're going to cause issues when it comes to that because you're only going to be able to dry to the interior. And those, if you have a lot of people using that bathroom, that's not going to be a good way for that wall assembly to dry. Here's another example of a 2x4 wall assembly with 2 inches of R10 XPS exterior foam. Um, we have our drywall, and you can see down here it's an R13 friction fit fiberglass insulation, so there is no craft face paper on there. And then we have 2 inches of R10 XPS rigid foam on the exterior side of this. Potential for double class 2 vapor retarder here. Is this good is the question. Remember, where is your throttle? The first part here is you have 2 inches of R10 rigid XPS, which is a 0.7 perm max per inch. So this is a class 2. Our fiberglass bat insulation does not factor in because it has no facing on that. There's no paper facing on that. Our drywall with latex paint is equal to 6 perm, so that's a class 3. And there's a house wrap on there as well, but that is very vapor open. That's well above 10 perms when we talk about permeability. Again, where is your throttle on here? I mean, I think the most restrictive part of this is going to be on the exterior side, is where your insulation is, your exterior insulation, but that's still a class 2, and that's still vapor open to the exterior. It's not as open as the interior side here as the class 3, but it can still dry to that outside. So this is a good assembly as well. And I think there's kind of like I would say a rule of thumb on this. If you're going to be, this is a rule of thumb. That's exactly what I want you to take this as. If you're going to be putting exterior insulation on your house, I think ideally 1/3 of your total R value insulation should be within that exterior continuous insulation. So yeah, so this right here definitely meets that. Drying potential. Assuming any assembly will get wet, will it be able to dry? And I talked about that a couple of times. I like to always imagine, yes, we are somehow going to get moisture within that wall cavity. Maybe something will happen on the exterior. Maybe somebody will do some construction. Maybe, I don't know, there is some way that a penetration happens that allows moisture to get into the interior of that cavity. You get a leak at a window, anything can happen. Assume that the worst is going to happen. Can that wall assembly dry? And that's the benefit of being able to dry in both directions, is if moisture does get into there, yes, we are going to see the ability for that moisture to pass out of that assembly as quickly as possible. And how does insulation placement, especially exterior insulation, affect that? What it really is going to do is it's going to affect the face temperature of your sheathing. And in this diagram here, you can see, there's little blue lines there. I'm not sure if you can make those out, but those are just temperature gradients. You have warm, moist air on the interior side of this building, and it's passing through, and that air is carrying some moisture with it. And it's coming toward the exterior side of this wall assembly, and it's going to meet a point there potentially of condensation where it gets cold enough within that wall assembly that moisture that's being carried through condenses into bulk moisture. We no longer have vapor moisture, we have bulk moisture. We have water within your wall assembly, and it can be a lot. You can get a lot of condensation within a wall assembly. I mean, just think of putting a can of soda or a cold can of something outside on a hot day, and it gets very wet. That moisture is not coming from the inside of that bottle. It's coming from just the general air, the humidity and the moisture level in the air coming in contact with that small bottle or a can, and there's a lot of moisture on there. And what do we do to mitigate that? You get a little koozie and you stick your beer or your soda in there, and it sort of helps eliminate that condensation. Think of it like that. Um, and so yeah, so what this does is like, yeah, where is this potential point of condensation happening? Um, and here it gets down potentially here to the exterior sheathing. And the thicker we get our foam, the heavier R value we have of continuous exterior insulation. We're really trying to mitigate that condensation point. We're trying to move that condensation point from your sheathing, from the interior face of your sheathing, the sheathing that's attached or contacting your fiberglass insulation. We want to eliminate that being a cold spot. And continuous exterior insulation is going to help do that. It's going to help move that condensation, that dew point away from the interior face of your sheathing, and make that sheathing warm enough that that moisture can't potentially condense there. Obviously, if we hit a cold snap where it's 0 or -5 for 5 or 10 days, it's gonna get cold in there. But hopefully it's gonna be very rare and it's gonna happen in such short amount of time that when it does condense in there, we have a vapor open, a building envelope that can dry in both directions, and that will happen. When those fail points do happen, we've planned for that, and we can now get that moisture out as quickly and as efficiently as possible from our wall assembly. Now we talk about materials. What material should you use for continuous exterior insulation? How will the addition of continuous exterior insulation affect your current wall assembly detail? If you're already building a wall and you're like, all right, I'm just going to slap this exterior insulation on the outside, I'm going to be okay. You want to make sure, like, all right, if I'm using this type of insulation, and this is what I'm doing currently, and I don't want to change that, you know, take the time and understand the material you're going to put on the outside of that and how it realistically is going to affect the total performance of your building envelope. Look at your window details and how you're flashing those and how those are going to be affected. In your siding details, are you attaching your siding directly to your sheathing? Are you going to need to install battens in there to allow a drying and an air gap in there so your wall assembly can dry a little bit easier and quicker? Um, is this material you're going to be attaching to the exterior of your house? This foam board, can it be exposed to the elements? Some of this stuff can't be. Some of this stuff has to be covered up immediately or as fast as possible. Some can be exposed for months and it's not going to be a problem. So, however you move through your building process, um, you know, picking the material is going to be important. Difficulty of installation. Do you want to spend a lot of time training people um, how to do this? Or is this just what's the easiest and the quickest method for doing it? And cost. You can buy I would say relatively inexpensive material off the shelf at Lowe's, or you can go to a much more uh, type of exterior insulation material that you can't find on the shelf, but it's very high performance and it has other benefits beyond just insulating as well. Determine your project goals for your CEI and how it affects how its characteristics will affect your project. Obviously, R value, the permeability, air barrier. What is your air barrier? Can your continuous exterior insulation also double as that as well? Water control. Can continuous exterior insulation also work to help control of water? Fire rating might be a potential or an area of concern in the health environment. What material you're using and how that it affects not only you, but the environment you're within. Most common materials used for continuous exterior insulation. Rigid foam boards are what we talk about most, but there's also mineral wool boards, which people might not be as familiar with. And there's high performance insulated sheathing, zips, and there's other forms of insulated sheathing out there, which means all it's saying is there is uh, sheathing that has already integrated the insulation within it. Here's a quick example of extruded XPS. Common use is sheathing. Yes, people do use it just as sheathing. It's also used as under slab insulation. Typical thermal resistance is about R5 per inch. Vapor permeability is 1 to 0.1 and up. So it's a class 3. Obviously, once you start layering those on each other, that will change. So if you get 3 layers of this, your permeability rating might not be class 3. It might drop to a class 2. And durability, that's another factor. This is something you don't want to have out for a real long time. Matrix is strong compared to EPS. It's more forgiving when you're using it. And EPS, this is like something we might be most common with. We think about cheap coolers. It's a little beads. Common use is insulated concrete forms. So you might, if you're using those in blocks and SIPs. Panels use this. It's about 4 R value per inch. It's a class 3 vapor retarder. It's at 5 perms. It's very vapor open. It's not very durable. You don't want to have this out exposed. It gets broken and damaged real easily. If you've ever seen it on a job site, you'll see it. Anytime you cut it, you're going to create these little beads that go everywhere. It's very hard to use and control the debris. Polyiso, this is most common use for sheathing. Thermal resistance is 6.5 per inch. It's very, very high R value. It's a very low paper permeability. It can be a class 1 depending on what type of facing it has on it. It could be a class 2 or a class 1. You want to make sure you read the exterior side of this. Whatever they have on there will determine what the permeability rating is. And durability factor, it's very, very durable, especially if you're using the foil face stuff. It's very easy to cut, and it can stay out exposed to the sun for a very long time. Some of the least common ones are a wood fiber board. I think there's at least 2 companies that manufacture this in the US. It's used as continuous exterior insulation. It's about R3.7 per inch. So it doesn't quite reach that R3.8 R value, which the new fenestration table references, R value table references, but it's close. Vapor permeability, it's very vapor open. It's a cellulose-based product. So it's a very high permeability rating. Vapor can pass through this very easily. It's a very sustainable product. If that's something your clients are really interested in and they want to be sustainable, it's very, very low carbon footprint. It's actually carbon negative. So it sequesters carbon. If that's something that you're interested in, this is a good product for that. And there's far fewer harmful chemicals that are used in the manufacture of this product than some of the foam products that you see out there. And rigid mineral wool, people might be more familiar with this than the wood one. It's used, again, as continuous exterior insulation. Our value fluctuates from 4 to 5 per inch. It's very vapor open. You can see here it's between 30 and 35 perms, which is very good. It's very fire resistant and pet resistant as well. So especially if you're in California, we're not in California, but if that's something that concerns you, fire rating this is a very good fire rating product. And here's just a few different examples of these products being installed. Installation details. Now this is I won't get too much into this just because there's 10 different ways to do one thing. We all know this when we talk about installing anything or building anything in the construction industry. You can give one example and somebody else can have an example of the installation, and it's just as good, but it's not like yours. What you want to always consider is your details around your windows and your doors. Penetrations are important to take into consideration, and do a lot of pre-planning, especially if you're moving into a new product that you haven't used before. The pre-planning stage is going to be the most important thing for you guys to take advantage of and really plan out these details and as best as you can. And we talk about when we start putting insulation on the exterior side of buildings, this is a diagram from Fine Home Building. It's a very good diagram. I like it. and it talks about how to install this type of insulation with a flanged window. And there are details like, yeah, you're going to need to buck out your sheathing a little bit. You're not going to be able to attach your flange directly to your continuous insulation. So those details are going to change a little bit. Um, you just want to be careful of what you do with that as well. And then there's also the flangeless window option detail as well. So these are least common windows to install. Most people are familiar with the flange windows, but flangeless windows are out there and you can use them. And especially when you start getting to much thicker wall assemblies, you might want to push that window in a little bit into your detail. And so there is a way to do these installation details. And again, there's 10 ways to do the same thing. They're all correct, but they're all just different ways of doing it. And it's going to take some planning on your part to figure that out. I included some details for your handouts, and you can reference these a little bit if you want to look at these moving forward. It gives you a sort of a jumping off point of things to consider when using exterior insulation. And determining, do I want to do an inset or an outset window and that sort of thing.